Hello everyone, welcome to Simio Sync 2022 Practical Applications Conference. Let me quickly introduce myself. My name is Devdatta Dev. I work as a senior engineer here at Simio. I'm mostly involved in simulation-based scheduling projects. And today we'll be talking about the mixed tank fill template. This template deals with systems where that are commonly used in the consumer goods manufacturing industry. So we will start with what is a template and how it can support model development and deployment. Then we'll move on to the mixed tank fill template itself, talk about the data schema used for the template. We will switch over to the model and discuss model layout, objects used in the model, and process to generate the model. We will also discuss how processes are structured to run the model, considering business logic, operational logic, and last but not the least, discuss output generated by the model. So let's start with what is a template. Templates are essentially models with flexible data schema that provide a starting point for model development. As templates can have majority of requirements already implemented, it can speed up the process of model development and deployment. We will be talking about data schemas more in the next few slides. Data schemas are essentially used to interface with Simio model to generate production schedules. Even though data schemas are predefined, users are not restricted to only those tables and columns. Based on the requirements, users can decide to add or remove tables or add or remove columns from the existing tables. So let's talk about the mixed tank fill template. There are many systems where there is a limited buffer space between upstream and downstream resources. Coordination between upstream and downstream depends on the utilization of the buffer space. This is the mixed tank fill template. There are mixers upstream that produce and transfer the product to a buffer location, which in this case is a collection of tanks. And there are downstream filling lines that consume from the tanks. Some constraints that are included in the template are tank cleaning, resource constraints, material constraints, and efficient campaigning with dynamic dispatching rules. Templates use modular processes and could be easily extended to support similar operations with different business rules, different operational logic, or different capacities. Next, we will look at the data schema for the model. Before we do that, let's quickly talk about tables in Simio. For those who regularly use Simio or who have used Simio in the past, this will be a quick refresher. Simio model can have two types of tables, essentially, input and output. As the name suggests, input tables are used to drive the model and output tables are used to display results as the model runs. Further, input tables could be collection of properties, states, or targets. Input tables can hold data imported from external data sources like MRP systems, ERP, or MES systems. Output tables are a collection of states to which values can be written to as the model runs, and these tables then can be exported back to external data sources like MRP or ERP systems or to a SQL database. You can also add target columns to table to track schedule performance like on time or on budget and so on and so forth. This next slide just gives an overview of tables used in the model. As you can see, this model has 25 input tables and 8 output tables. We can generally divide input tables into operational and transactional tables. Diagram on the right hand side of the screen lists all the relational tables used in this model along with foreign key relationships. We'll be talking about these more during the next few slides. Now let's take a quick look at some of the important tables that are used to generate and drive the model. Let me quickly switch over to Simio. So these are all the tables that are used in this model. I'll talk about some important tables in the model. So let's start with the resources table. So this table is actually used to generate this model. So this is what we call a concept of data generated models. Each row here represents the resource that is being used in the model along with the resource type. And so if you want to create a new resource, then you just add a new row here and Simio will automatically generate that resource at the specified XNZ location along with all the default properties. This provides an immense flexibility in terms of quickly updating the models when your system changes. So if there is an external data source, then you can map this table to that source. And once it's updated, your Simio model will also get updated based on whatever changes that have been made to the system. Next, we have materials table, which is essentially a material master table, which lists all the materials that are used in the model along with their attributes. So this actually helps us drive the model in terms of changeovers, in terms of batch cycle times, case fill rates, so on and so forth. We also have bill of material table. And in this particular template, we have just defined bill of materials for the top level components, that the products, that is the FG SKUs. But this table can be easily extended if needed to include bill of materials for lower components or for other raw materials. So based on the system requirements, you can update this table easily by connecting it to an external system. Besides this, we have setup transition table, which lists the changeovers that need to happen as we switch from one product to another. So, for example, if we switch from an FG SKU, which is 100 mLs to 250 mLs, then it takes us about 7.1 minutes to do that changeover. We also have tables that list schedules for operators and for resources. So we have a day schedule and we have a night schedule for operators and a separate schedule table for resources. We also have a couple of tables that list the work in process. So we have mixing work in process, we have filling work in process, and we have initial whip tank inventory. So these tables help us update the model to the current state of the system, and then it can be used to run the model, to drive the model and generate a feasible schedule. Before we talk about how this model runs or works, let's quickly take a look at the Simio version that is used to develop this model. So this model is developed using Simio RPS edition, which is our risk-based planning and scheduling edition. RPS edition is used to develop process digital twins. RPS allows for dual use of simulation model to generate both detailed resource constrained deterministic schedule as well as probability based risk analysis. This template uses product based routing. That is, routings are based on materials and not on orders. And as I said earlier, we use data generated and data driven modeling approach for this template. Now let's quickly go through the facility layout. As you can see, this is a simple system with two mixers on the left, set of tanks in the middle, and fillers on the right. So the way this system works is the product is mixed in the mixers and transferred to the tanks where it is held until it can be consumed on the fillers. We also have a couple of transfer nodes where routing decisions are executed. To the left of mixers, we have a mixing node where we decide which orders to route next to the mixers. To the left of the fillers, we have filling node, which decides which orders should be routed next to the fillers depending on the constraints and the availability of downstream fillers. At this point, let's also talk about objects used in this model. This template uses 7 custom objects. These have been subclassed from standard library objects. For example, MES mixing and MES filling are based on standard library server object. Similarly, sched worker and resource object are based on worker and resource object respectively. In some cases, objects were customized so we could add states and properties that were needed, but mostly objects are customized so that users can, if needed, easily modify these objects to suit their requirements. This again simplifies the process of model development. This model also uses 3 different entity types. So we have MO ordered entities, which are actually the FG orders in the system. Then we have mixing orders. These are the component orders that are routed to mixers. And then we have filler orders. These map again to MO orders and are routed to fillers for filling. Next, we'll take a quick look at the elements that are used in the model. Simio uses elements to implement changeovers, materials, routings, constraints, etc. All the elements can be auto-created from tables. For example, material elements are auto-created from materials table, along with default properties for those elements. So here in this model, we use 2 changeover elements to implement changeovers for mixers and for fillers. We also have a couple of constraint logic elements. We'll talk about these a little later when I describe how the model works. We also have routing groups that are used in the filling and mixing transfer nodes to dispatch orders. And we also have a couple of state statistic elements that are used to track model performance. So now let's talk about how this model actually works. As we saw in the previous slide, this model uses concept of data generated and data driven modeling. So now let's see how that is actually implemented. So we have a manufacturing orders table which acts as an input to this model. These orders can be specified over a planning window, and the planning window could depend on how the planning process is executed at a particular location. So, for example, a planning window could be weeks worth of orders released simultaneously, or a month's worth of orders, or in some cases, it could be just 1 day's worth of orders. Once these orders are generated, and released to Simio, they are transferred to the MO order queue where they sit until all the components are processed and all the cases that are required for each order are filled. So once the required number of cases are produced, the orders are marked as completed. We update the ship date in the manufacturing orders table and the orders leave the system. So this is just a brief overview of how the route controller object works. Now let's take a look at how we generate component orders. So as I said, we have manufacturing orders table, which drives the model. So on initialization, Simio looks through the demand provided in the manufacturing orders table and accounting for work in process in mixers and tanks and fillers, we calculate the total requirement for the product associated with that order. This quantity is then calculated for each product and then converted to number of batches based on the batch size. Uh, and all the data required for that is defined in the material master table. These batches are then pegged to MO orders. Batches can be pegged to multiple MO orders. So, for example, if batch size is 5,000 kgs for a certain product and we just need 3,000 kgs for one FG order, then the remaining 2,000 kgs can be assigned to some other FG order as well if needed. So, once these entities are generated or created, they are transferred to the mixing order queue where they sit until they can be dispatched to downstream mixers for processing. This again is done by using routing group logic. And and there are a couple of constraints that we have to make sure are satisfied before the orders can be routed. So one constraint is a secondary resource is needed at mixer. So if that resource is not available, then the orders cannot be routed. And the other thing we check is whether web tanks are available to actually transfer the product once the batch is finished. So we don't want to start mixing anything if downstream web tanks are not available. So if once these constraints are satisfied, mixing orders are transferred to the mixers and then they will undergo their batch cycle operations. The batch cycle time for each product is again defined in the materials table. Once the batch is finished processing, we transfer that batch to the web tank. And it will sit in the web tank until it can be consumed on the filling lines. So now let's talk about the filling operations. So once the batch is ready, once the mixing batch is ready and as it gets transferred to the web tanks, we trigger a process which generates a filling entity, and that filling entity will be transferred to the filling queue. If the mixing batch is pegged to more than one order, then we will generate more than one filling entity associated with each MO order. And from the mixing entity, we already know the amount of cream that the batch has, and then based on the size of the case for the FG order, we can calculate number of cases that can be produced from that batch. So this data then gets updated on the filling entity, and the case fill rates are already defined in the rate routing table. So once that data is available, the filling entity will then get routed to one of the downstream fillers, again if certain constraints are satisfied, which in this case are a material constraint. Because we are filling, we need to have bottles available before we can start filling operation, and we also need a secondary resource. So if both of those conditions are satisfied, we transfer that entity to the filler, and we can start the filling process. And as we run this model, you'll see the animation as the cream gets consumed from the web tank. As I had said earlier, we have mixing batches that are pegged to filling orders, and each filling order could have multiple mixing batches based on the requirement of the order. So each mixing batch is produced, we produce corresponding filling batches and transfer them to the filling queue. This model also has a constraint where once we start filling a particular FG order on the filling lines, we will try and make sure that we produce the same FG order on the filling lines until we completely process that FG order. We won't switch between the FG orders to reduce the number of changeovers. Similarly, we also ensure on the mixing lines, if we start mixing product for one FG order, we'll try to make sure that we completely produce the entire product required for that FG order before we switch to any other product. This just ensures coordination between mixing and filling, and also ensures that we utilize our web tanks correctly and we don't do any unnecessary changeovers on the web tanks as well as on the fillers and on the mixers. So let me quickly run this model just to show how the animation looks as we run the model. So here you can see we have mixing orders that are waiting in the mixing queue. We have filling orders that are waiting in the filling queue, and we have a couple of orders that are currently being filled. So if I switch to 3D view and run this model, you can see cream is being consumed from the big tanks. So let me quickly fast forward this model now. So this shouldn't take too long to run. So as you can see, now we have processed all the MO orders. And if you look in the MO orders table, you can see we have updated the ship date for all these orders. And now we can use these target columns to check if the order was shipped on time or not. We will look at some of the dashboards and output tables that are added to the model to track model schedule performance. So let's quickly jump to some of the dashboards. So first, let's take a look at schedule performance. So here you can see 100% of the orders were processed on time. None of the orders were late. We also have a changeovers table, which just lists the number of changeovers that we had to do during the week, and also provides details of the changeovers. So the location, the previous material, current material, starting time, and end time. We do this for all the resources. So fillers, mixers, and web tanks. And we generate this Gantt as the model runs. So this is a resource Gantt, which shows what each resource was doing as the model ran. So for example, on mixer one, we started with this particular order. This was a whip order. So if you look at the details, you can see this order was already in process when we initialized the model. So we started first with that order. Then we switched to a different order. But we tried to make sure that it was the same material as we wanted to avoid changeover. So this data is displayed for each resource, and this can be exported to an external data source, and then it can act as your operational planning board for the plant. So we have considered a couple of different scenarios here. So this was the base model. This is a different scenario where we have added an unplanned downtime or exception. So you can see here there was a downtime on filler 3, which was a 12-hour long downtime. So we had to stop production on filler 3, and then the order had to wait till the resource came back online. And we can easily see its impact on schedule performance. So you can see over here our schedule on-time performance went down to like 94.5%. So we had 3 delayed orders. And finally, we have a scenario where we are looking at a situation where we don't have enough critical materials to complete our FG orders. So as I mentioned earlier, this model uses bottles as containers to fill the cream in. And if you don't have enough bottles, then the orders cannot be processed. So here, this is the initial inventory of the bottles that we have in the system when we initialize model. And for these bottles, we have actually defined what's the replenishment quantity, replenishment point, and replenishment lead time. And then if you look at the material element itself, we are following a continuous review period and a replenishment policy of reorder point and reorder quantity. So once we hit a certain level of inventory for these bottles, it will trigger the replenishment process, and then based on the lead time, orders inventory will be refilled, and then we can continue processing orders. So now if you look at the Gantt or at the schedule performance, you can see it actually went down to 65%. So this just indicates that the initial inventory that we had was not enough, and then we ran out of some of the critical material, and we had to wait. So this just gives planners transparency into why certain orders were delayed and what they could do. So, for example, they could change the replenishment quantity or replenishment point of the order so that the material is ordered early, or mm, and they could switch the priority on some of the orders so that they have enough material available to fulfill those orders. So I think this pretty much concludes my presentation. We have some time at the end for question and answers. Thank you so much for attending this session.
Hey, Dudada, good morning. Thanks for that great presentation.
Hey, good morning, everyone. Can you hear me?
Yeah, I can hear you just fine.
Okay.
Yeah.
Hey, Adam.
So we got some good questions here from the audience. I'll go ahead and just jump into them here. The first one is around just scheduling in general. Can you elaborate how you would use a model like this for scheduling? I know you mentioned it briefly on at the end there on kind of like manipulating some different replenishment policies, but can you think of any other use cases where you would use a model like this for scheduling?
So couple of different use cases, like for example, because this is a digital twin, so we are connected to the system real time, right? We're importing data from the system as the system is working. So now we
Mhm.
can get updated inventory information. So if you have any critical materials that you're keeping track of, or because of supply chain issues, certain components are not going to arrive in time, then you can use a model like this, right? You can quickly re-import all the latest state of the system, get the data and rerun the model, and now based on your current inventory position we can schedule. So we'll take into account if there are any shortages. We'll also take into account if certain components are getting delayed, right? Because you
Mhm.
can specify lead time. So if I update the lead time and then say now it's going to take 3 weeks instead of 2 weeks, now we can plan accordingly. Another aspect is failures.
Mhm.
If a line goes down, then what do you do? And now you can change the. So let's say, for example, if a certain line goes down and you have certain orders that are higher priority, then you can make sure that you can bump up their priority so they get scheduled at the right time, because you don't want those orders to be delayed.
Sure, sure. That's great use cases. Thank you for that. So one here is kind of talking about the template. Is there any other use cases other than the consumer packaged goods where you could see this template being helpful?
So I think that's one of the biggest application, at least for this model. But
Hmm.
besides this template, we also have other templates that are more applicable to some other discrete systems, right? And even this template could be applied to other discrete systems where you have similar setup, where you have constrained buffers in between your
Hmm.
upstream and downstream production. So it's not really restricted to templates, or rather just the mixed tank field, right? It could be any consumer packaged good. So you could replace those tanks with queues or with
Hmm.
warehouse with racks, and you
Okay.
can track the consumption or the inventory levels in those racks. So it's really not restricted to just CPG sector. But the focus of this template is on that, but you can definitely
Sure.
modify this. You have tables that you can use, and that makes it a lot more easy to extend it to other similar systems.
Sure, sure. So pretty much any system that would have process, buffer,
Right.
process, you could apply that
Yeah.
understanding to. Yeah, that's great. Okay, thank you. So could you elaborate a little bit on how the constraints are considered before routing the entity at the mixing and filling node?
Yeah, sure. So what we do is, especially for mixing, at least in this template, we have only considered two constraints. So one of the constraints that we check before we route an order is, do I have enough secondary resources available? So if I need an operator to actually operate those mixers, so I make sure that I have an operator available before I can route, and that's part of our resource constraint. And the other constraint is we check if I'm going to have enough capacity available in the web tanks to actually transfer that product. If I don't have enough capacity in the web tanks, then I just end up blocking that mixer. So I cannot. I could have processed something else and could have stored it in a different web tank, right? So I want to avoid a
Sure.
situation where I unnecessarily block those mixers, because I have limited number of mixers and I have a large variety of products that I need to produce in those mixers.
Yeah, makes sense. Makes sense. And just to clarify, that's all really done through the constraint logic element, right? And then applied to the nodes, routing constraints, and
Uh,
those properties. It's all
right.
done through
So
that. Okay.
for resources, it's done that way for
Hmm.
secondary resources, but for web tanks, we actually do that check as part of our routing add-on processes. So that's done
Oh,
in
okay.
the on evaluating route request process.
Great. Oh, great. Okay. So kind of two different methods for
Yeah.
applying the constraint.
Mhm.
That's great. Okay. So this one, it says it seems that there's a combination of discrete object and flow objects used in this template. Can you explain how you utilize these different object types to work together?
Yep. So this is essentially we are mostly using discrete objects here. So what
Hmm.
we do is we create those orders as discrete entities, and then just for the purpose of animation, actually we when we transfer those batches to web tanks, we just convert them to flow entities. So those
Okay.
flow entities are actually just used for animation. Pretty much everything else in this model is a discrete system. So you can, if you are not interested in animation, you could essentially treat those as discrete entities as well.
Okay. Okay. But there is like the flow entities kind of, I guess, flowing into the fillers as it's filling the discrete parts.
No, so what we do
Okay.
is when you're filling anything in the fillers, we just assign flow rate on the output node of the uh, web tank itself, and then
Okay.
that flow just goes into sync. It's not doing anything. So
Okay.
it's just animating consumption from the web tanks.
I see. Okay. Now that makes a lot of sense. Okay, we have another one from the audience here. I think this may be one of the last few here. This one just says, is there a maximum number of input or output tables that can be used in this template?
No, you can add as many tables as you want to, or if you feel that some of those tables are not necessary for your operations, you can get rid of those tables.
Great, great. Yeah, and you can expand on the
Yeah,
size of those tables as well as
right.
needed. Okay, great, great. Okay, well, I think that's actually all the time we have for questions. So thanks, DevData, for again the great presentation here, and thanks for being a part of Simio Sync.
Yeah, no problem. Thanks, Ryan. Thanks, everyone.